So you know that before the mint we finished up to sample and hold circuit. So that was the primary step of analog to digital conversion. Now to obtain a digital signal from an analog signal, the quantizing and encoding operation also has to be completed. So here we are going in today's lecture we are going to discuss about two types of ADC circuits that could be used to do that quantizing and encoding operation. So the first type that I'm going to discuss now, that is the called the flash AD converter. So in this flash AD converter, there are normally 2 to the power n number of resistances used to form a ladder network which will work as a voltage divider at multiple stages, where n is actually represents the number of bits that you will have in your equivalent digital output. So along with uh, these 2 to the power n registers, there will be a ladder network which will uh, generate unique reference voltages which will be used uh, to compare using a comparator circuit. So in terms of circuit diagram, okay, let us assume a 3-bit flash AD converter. So for a 3-bit flash AD converter, you can say that there would be 2 to the power 3 or 8 total resistances which are indicated over here, 8 equal resistances. So they are actually working as voltage dividers, and reference voltages are the this reference voltage is divided into multiple segments, taking the I mean voltage drop from each intermediate node. So for the first node, you can easily say that if you consider the voltage divider, you can say that this would be your voltage at this node. Now here you can easily cancel the R's. You can say that 7 by 8 VR, which is actually equals to 0.875 VR. In this way, similarly, the reference voltage is actually divided into multiple stages, and each of these reference voltages are connected with a particular comparator circuit. So the op-amp here is working as a comparator. So each of these unique reference voltages are connected at the inverting terminal of each particular op-amp, which are working as comparators. And the non-inverting terminal of each of the comparator here is directly connected with the analog input voltage. Now this analog input voltage is actually the analog voltage after it is passed through a sample and hold circuit. So then that portion of the analog signal is connected with the non-inverting terminals. Now for a comparator, you know that if you have two different voltage levels at the non-inverting terminal and the inverting terminal, so if V1 is greater than V2, the voltage at the non-inverting terminal is higher, then at the output side you are going to get a high signal. Otherwise, if the relation is reversed, then you'll get a low signal. So each comparator is either going to give you a high signal or a low signal depending on the voltages at the two terminals of each comparator. So the output of each comparator will later on be connected as an input to this priority encoder. So the priority encoder, depending on the input bit pattern, it will generate an output bit pattern as well. So that final output will be taken from the priority encoder. So here it is a 8 by 3 encoder, So when you're giving 8 bits as your input, and at the output side you're getting bit sequences of 3 binary digits. Now the operation of priority encoder, do you guys remember how the priority encoder works from your digital logic course? I think you studied the priority encoder. Can anyone suggest?
If the bit at I7 is 1, then the output will be 111.
If
And
what will happen if I5 is 1 and also I7 is 1?
then I7 will be counted, I guess.
Okay, so that indicates that the highest significant bit that is equal to 1, that will be given the higher priority, right?
Yes, sir.
So that is the case in case of priority encoders. So the truth table will be much more easier to demonstrate. So like your friend suggested, so whenever a higher significant bit is 1, then all the lower significant bits, for the lower significant bits, don't care condition will be considered if the higher no other higher significant bit is equal to 1. So depending upon which highest significant bit or higher order bit is equal to 1, a particular output sequence will be generated. Suppose if D0 is equal to 1 and none of the other higher bits is equal to 1, all of them are equal to 0, then you are going to have 0, 0, 0. In case of D1, if it is equal to 1, then doesn't matter what is the state of D0. If all the other higher bits are equal to 0, then you will have 0, 0, 1. In this way, the priority encoder will give priority to the higher order bit that is being set to 1. So in this way, the outputs of the comparators will be fed to the priority encoder, and the priority encoder will convert that into a 3-bit sequence. So this 3-bit sequence will be the final representation of the analog input that is being connected in this particular arrangement. Now, the initial bit or the LSB of the priority encoder, it can be directly connected to a high state without connecting an intermediate comparator, because it is not necessary in this case, because if it is set to 1 and none of the other bits are comparators are giving you a high signal, then you are going to get 0, 0, 0. So for that reason, there is no need to connect a separate comparator for the LSB. However, for the other bits, it is necessary to connect a comparator to compare it with each particular reference voltage levels. Now, I said that the analog input which is connected over here, that is the analog signal after it is passed through the sample and hold circuit. So this arrangement is actually doing the quantizing and encoding operation. So definitely you can now suggest that the what is the purpose of a quantizer, that uh, it actually creates a finite level of uh, quantized states. So that operation is actually done over here, where you are providing a unique reference voltage, and each unique reference voltage is actually suggesting to a particular quantizer state. And later on, using the priority encoder, you are actually doing the encoding operation, where you are encoding the analog signal finally into a bit string. So this is the general operation for this particular arrangement. Now, if I talk about the advantages and disadvantages, so some of the advantages are that the operation of this particular arrangement is relatively faster compared to the other ADCs. And also, as you have seen, that the operational theory is also quite simple, and the speed, this gives you a very faster speed. So only the limitation factor for the speed is the gate or comparator propagation delay, but that doesn't have too much of an effect. So a relatively faster response can be obtained compared to the other ADCs. Now, about disadvantages, you can suggest some of the disadvantages by yourself, because you have seen that for n bit of uh, uh, n bit of digital output, you need 2 to the power n number of resistors and 2 to the power n minus 1 number of comparators. So suppose for 3 bit you required 2 to the power 3 or 8 number of resistors and 8 minus 1, that is total 7 comparators. Now if you want to increase the resolution of the digital output, you want to increase the number of bits. So if you consider 4 bits, then you would have 16, require 16 number of resistors and 15 comparators. So increasing 1 bit at your digital output actually almost doubles the requirement of the number of resistors and the number of comparators. If it is 5 bits, it will again uh, double compared to the 4-bit case. So which will require the size of the circuit to increase with the number of bits, and more components will be necessary, which will actually uh, increase the cost as well. So the expense and the requirement of the number of components for the higher number of bits becomes one of the disadvantages for this sort of design. Now moving on, the other type of ADC that I am going to discuss in today's class is successive approximation analog to digital converter. So first of all, for this particular type of ADC, I can start discussing about the different components that are necessary. So they are the successive approximation register, a special type of IC, a DSC, which is a digital to analog converter. So the successive approximation register is shown over here through using this particular block. The digital to analog converter is shown over here, and there is also a comparator in this design as well, indicated over here. So these are the main components of this particular type of ADC. Now, how does the design actually operates? So the successive approximation register, it actually generates some sequential bit patterns. So that corresponding bit pattern gets converted by the DSC. The digital bit pattern is converted into an equivalent analog voltage, which is represented over here by VDA. Now that VDA is compared with the original input signal after it is passed through a sample and hold circuit. So the VDA and Vin, they are compared through the comparator. The comparator sends some feedback signal to the SAR, and SAR takes some decision what would be the next possible bit pattern. Now, to elaborate a little bit more, the successive approximation register actually checks each bit at a time. It starts from the MSB. It tries to decide whether the MSB should be set to 1 or 0. When it decides about the MSB, or the decision of the MSB is taken, what state should it be. Then it moves on to the next bit and tries to decide what would be the state of this one, whether 1 or 0. In this way, successively it checks all the n number of bits, okay, up to the LSB. And at each cycle, it decides whether that particular bit should be set to 1 or it should be kept at 0. So this register SAR operates with respect to a clock pulse. So suppose for each pulse, for each pulse or each period of a pulse, a particular bit is checked. So for the first pulse, let's say the MSB is checked. For the second pulse, the next bit is checked. And for each cycle, uh, the bit pattern is converted into its analog form. The analog form is compared with the original input voltage, and depending on the comparator output, the SAR decides whether to keep it to 0 or set it to 1. Okay, so in the first stage, or the first cycle, let's say, the SAR sets the MSB equal to 1 and keeps all the other lower bits equal to 0 at the initial stage. So here for n bits, there will be multiple intermediate bits as well, but all of them would be set equal to 0 at the initial cycle, except the MSB. So when the MSB is set to 1 and all the other bits are 0, with respect to this particular bit pattern, the DAC is going to generate a equivalent analog voltage, that is VDA. Now the comparator is comparing VDA and Vin. So if VDA is actually less than the input voltage, then the SAR will decide that the MSB should be kept at 1. Or if VDA is greater than Vin, then the SAR, the successive approximation register, will decide that the MSB should not be kept at 1, it should be cleared to 0. So suppose this is the first cycle where the MSB is considered. So when one of the decisions is taken for the MSB, either 1 or 0, depending upon the comparator decision, then in the next clock cycle, the SAR will shift to the next possible bit, and it will set this next possible bit to 1 and check whether it should be kept at 1 or it should be cleared to 0. In this way, sequentially or successively, it will check all the remaining bits up to LSB, and at each cycle, the decision for that particular bit is going to be checked. And when all the bits are checked, and signal will be provided to this particular pin, which is actually called end of conversion. So when all the bits are checked, which means that the final bit pattern is obtained, that is the equivalent digital output for this input signal, then a confirmation can be taken from this EOC pin, which may be used to actuate some other portion of any connected circuit. Now, an example of a 3-bit successive approximation ADC might be a little bit helpful to get a better insight about the operation of this particular ADC. Now, for the 3-bit successive approximation ADC, the SAR is supposed to generate 3 bits as its output, and those 3 bits is going to be working as an input to this DAC. So the DAC with respect to the reference voltage is going to provide a particular equivalent analog voltage for a particular bit pattern. So for this example, if we consider that the reference voltage is equal to 10 volts, so for 3 bits we can say that there will be 8 states, 8 quantizer states, and 10 divided by 8 we can easily determine the quantization interval as well. So from each bit sequence to the next sequence, the jump will be 1.25. So if we start from 000, that is said, that will give us an analog voltage of 0 volts. Then for 001 we are going to have 1.25. In this way, in each quantizer state there will be a jump of 1.25 volts. So up to 111 we'll have a voltage of 8.75. So in the first cycle, the SAR is actually going to check the MSB. So let's consider the 3 cycles, and another assumption for this particular example is say that the Vin is equal to 3.2 volts. I mean, when the input voltage is passed through the sample and hold circuit, let's say that for a particular duration the voltage is kept constant at 3.2 volts. So our target would be to get a resulting bit pattern for this 3.2 volts. So the 3 cycles, so for the first cycle the MSB is going to be considered. So here the MSB is set to 1, keeping the other lower bits equal to 0. So the input bit pattern to the DAC is 100, and according to the table which was shown in the previous slide, for 100 the corresponding uh, output of the DAC is 5 volts. So the VDA will give you 5 volts. Now this 5 volt will be compared with this 3.2 volts, and you can easily say that the VDA is greater than the input voltage. And as the VDA is greater than the input voltage, the MSB, the comparator is actually going to send a low signal because the input at the non-inverting terminal is higher. So it is going to send a low signal to the SAR, and the SAR is going to decide that it cannot keep the MSB equal to 1. It should clear the MSB to 0. So that should be the decision taken for the MSB, that it will set the MSB to 0. And the resulting bit pattern after this particular cycle will be 000, and in the next cycle a decision will be taken for the next possible bit. Now here I would like to ask you a question, that when our input voltage is less than the voltage provided by the DAC, why are we clearing the bit from 1 to 0? Why are we not keeping it equal to 1? So what can you infer from your intuition? Anyone? I'm asking that when this condition is satisfied, then why we are taking the decision that a particular bit should be cleared to 0? It should not be kept equal to 1. Okay, let's say that here our target is to reach V in. We want to generate a bit pattern that will correspond to the analog input voltage. So this is our target. And currently our VDA is the current representing the current state of this bit pattern. So if V in our target is 3.2 volts and we are now at 5 volts, we are ahead of the target. So in order to reach the target, we need to decrease the value of VDA so that we can have a bit pattern that is more closer to this target of 3.2 volts in this case. So we were at this stage now when the MSB was set to 1 and the other bits were set to 0. So if we keep the MSB equal to 1 and try to check the other possibilities of the states of the other bits, it will only increase our VDA. It will not decrease the VDA. But according to the current status, we need to decrease the VDA. So we need to go for a bit pattern that is going to decrease VDA. So that is only possible when we set the MSB to 0, because for these bit patterns, for these combinations of other uh, 2 bits, you may get a value of VDA that is closer to 3.2. So 3.2 is actually in between 2.5 and 3.75 over here. So you need to go towards this direction over here. So you should clear the MSB so that you can have a bit pattern that will give you eventually a lower VDA that in this case will lead you towards your desired voltage of 3.2 volts. So similarly for the other 2 bits, the same technique is going to be followed by the SAR, that it has now already decided what should be the status of the MSB. Now to check or take decision about the next possible bit, it is going to set the next possible bit equal to 1. After setting the next possible bit equal to 1, this is the bit pattern that is going to be working as an input for the DAC. So the DAC is now going to again generate a corresponding output voltage of VDA. So that is 2.5 volts according to table 1. So now the input voltage is greater than this voltage of VDA at this particular cycle. So the SAR will decide that it can keep D1 to be unchanged. So the resulting bit pattern after the second cycle will be 0, 1, 0 as indicated over here. So lastly, the first 2 bits have already been considered. The last status of the last bit is now going to be checked. Now similarly, now D0 is going to be set to 1. The input bit pattern to the DAC would be 0, 1, 1, which will correspond to 3.75 volts. And as 3.75 volts is greater than the V in 3.2 volts, the SAR will set D0 equal to 0. So final bit pattern that you are going to get after the 3 cycles will be 0, 1, 0. So for this particular 3-bit successive approximation ADC, for 3.2 volts, you are going to get a digital bit sequence of 0, 1, 0. Now, as there are only 3 bits at the output, uh, at the digital output, and the reference voltage is 10 volts, the quantization interval is to 1.25 volts. So this interval is quite large. So the quantization error will also be quite large, because according to the table 010 refers to 2.5 volts, and you are using this particular bit sequence to represent also 3.2 volts. So you can easily suggest that there is a high degree of quantization error present over here because of the only 8 quantizer states. Now, in order to increase accuracy, or by increasing the number of bits, which will improve the resolution of the ADC. Suppose if you go for 4 bits, the accuracy will be higher, the quantization error will be low compared to the 3 bit. For 5 bit, it will be even, the accuracy will be even higher, or the quantization error will be even lower compared to the 4 bit or 3 bit case. But as you increase the number of bits, what could be the possible disadvantage for this particular design? Can anyone suggest? Did you get my question, anyone?
No, sir.
I'm saying that in order to increase the accuracy or reduce the quantization error, suppose here I have discussed about 3-bit ADC. Now, if I want to go for 5-bit or 4-bit, 5-bit, or even higher number of bits, that will increase the resolution or increase the accuracy by reducing the quantization error. What could be the possible problem if we increase the number of bits in case of this particular ADC?
We need converters with higher bit capacity.
Well, obviously we need converters for higher bit capacity. The DAC that we would require, that would be necessary to be able to convert higher number of bits into analog, equivalent analog form. But one more thing is that the SAR checks or decides for 1 bit at a time. So if the number of bit is increasing, the computational time or the execution time will also increase for each number of bits that you are going to increase, because in each cycle it is going to check only 1 bit, and successively it is going to go for the remaining bits as well. So the slower execution time for higher number of bits could be one of the disadvantages for this particular design. Now, in terms of a tree diagram, the whole flow of this conversion process can be demonstrated. So in each stage, the analog to digital converter actually takes decision for one particular bit in case of SAR. So if we start from the MSB by setting it equal to 1, we, depending upon these two conditions, we may either decide to keep it to 1 or clear it to 0. So we will have two branches for the MSB. So if this condition is satisfied, it would be kept at 1, otherwise it would be cleared to 0. And after taking the decision from MSB, the next possible bit should be set to 1. And again, from each of these two nodes, there will be two separate branches deciding whether it should be kept at 1 or cleared to 0. After that, for the last bit, to check the last bit, that last bit has to be set to 1. And from here again, there should be two branches to decide, to demonstrate the full uh, possible states that can be obtained for a 3-bit scenario. So this diagram was not complete entirely. So from each of these nodes, again, two branches would be there to represent the possible states of the least significant bit. So I think you can later on complete it by yourself, considering the two conditions for each branch. Now I'll end today's discussion with an alternative approach that you can use to examine each of the cycles which were discussed in the previous slides. So in the previous example, or in the previous approach, initially what we needed to do was to formulate a table where we would have all the quantizer states and their corresponding analog voltages. But like it was shown in table 1, so we had to formulate a table that would represent each of the quantizer states along with its corresponding analog value. But for 3-bit, it was relatively easier to do because there were only 8 quantizer states. Now, if you consider 4-bit case, it would require 16 quantizer states. For 5-bit, it would require 32 states. For 6-bit, 64. So deriving a table of quantizer labels in this form would be very time consuming job to do if this approach is followed. So rather than that, the alternative approach can be followed where instead of deriving the entire table, a table can be developed where the contribution from each bit is going to be considered separately. So if I talk about D0, if it is suppose for 001 where the contribution is from only the least significant bit, for 10 volt reference, you can say that the DAC is going to be giving you 1.25 volts. For 010, it is going to give you 2.5 volts. For 100, 5 volts. So in this way, a table is formulated by considering only the contribution from each particular bit alone. So another way to easily formulate this table is to determine the quantizer state first, quantizer interval first. So here the reference voltage is 10 and the for 3-bit case the number of quantizer states is 8. So your quantizer interval is 1.25 volts. So for the first bit, the contribution will be equal to this quantizer interval. For the second bit, it will be double of the previous bit. So double of what you are getting from D0. For the third bit, the contribution would be twice of the previous contribution from the previous bit. In this way, for higher number of bits as well, by determining the quantizer interval, you can formulate a table easily where you would have the contributions from each particular bit. Now let's go back to the 3 cycles of AD conversion. So for the MSB, we can set it to 1, keeping the other bits equal to 0. So for 100, what would be the contribution from, equivalent analog voltage produced by the DAC? So here there is only contribution from the MSB. So you can add 5 plus 0 as there is no contribution from the other 2 bits. So you will have 5 volts as your output from the DAC. So similarly again like the previous case, this 5 volt will be compared with input voltage of 3.2 volts, and as the VDA is greater than V, D2 should be cleared to 0. So this will be the corresponding bit pattern. Similarly, for the other 2 cycles as well, after deciding for the MSB, the next possible bit would be set to 1. Then according to table 2, as there is only contribution from the second bit, the corresponding voltage would be 0 plus 2.5 plus 0. equals 2.5 volts, you can compare it with Vin and decide for what would be the state for D1. Lastly, for D0, you can set it to, the SAR will set it to 1, and for this particular bit pattern, there is contribution from the lower two bits, so you will have 0 plus 2.5 plus 1.25, which will eventually give you 3.75 volts as your output from the DAC. So this voltage VDA is going to be compared with Vin, and depending upon that, the ACR will take the decision whether D0 would be set to 1 or cleared to 0. So in this way, the same process can be examined. Instead of deriving the entire table, rather than deriving a table which will only comprise of the contribution from each particular bit. Now, some advantages and disadvantages of this particular ADC. So the disadvantage has also already been discussed, that for higher resolution, or where you want to increase the number of bits at your digital output, the process will be slower because it checks each bit at a time. And about the advantages, its speed and accuracy is quite reliable, and compared to the flash ADC where the cost is too high, if the speed and cost both of them are considered, then this particular design can be considered to be a good trade-off between both speed and cost. So these are some of the advantages and disadvantages of this particular ADC.
Sir, I have a question.
Yes.
When we are talking about ADC or DAC, is it not more flexible or logical to use the quantization error term instead of resolution?
Yes, I have also mentioned that, right? So in case of quantization error, you can say that for lower quantization error, success approximation ADC will be slower. And in this portion, I was trying to discuss about the quantization error, that for a 10 volt reference voltage, your quantization interval will be 1.25, which is a high interval. And from the prediction of this particular 3-bit ADC, what we are getting, the final bit pattern is 010, which actually corresponds to 2.5 volts. But using this bit pattern, we are representing 3.2 volts. So you can see that there is a large gap between the two values. So the higher quantization error is present over here. So in order to reduce the quantization error or increase the resolution, or improve the resolution rather, I should say, improve the resolution or improve the accuracy by reducing the quantization error, we have to increase the number of bits in our output representation. But increasing the number of bits will result in the process to be slower, because the successive approximation register sequentially checks each bit at a time. It doesn't check all the bits simultaneously. Any other question?
Sir, I had a question from the mid syllabus. Can I go for it?
Yeah, you can go for it.
Sir, in the mid syllabus, we classified the bridges, some for the medium range impedances or low range impedances. So I was saying that when we have a particular circuit material like inductor, capacitor, resistance, we don't know about its value or any information. So how do we know that we should measure it with medium range bridge or short range bridge? So if we just random choose any bridge, it will give a wrong result, right? So how can we resolve this issue?
Well, normally they are used for testing purpose. Suppose you are manufacturing a low range, suppose you are manufacturing a low range resistance. Suppose you want to check whether your uh, value of the resistance is how much closer to the standard resistance. So you have three arms which are fixed, right? Suppose in one of the ratio arms the two resistances are fixed, and in the other arm you have a variable resistor. So that variable resistor is actually going to work as a standard resistor. So you are actually going to try to check uh, uh, you are actually going to try to check whether the resistor that you want to measure, it is actually giving you the desired result or not. So in most of the cases that is the case, that you want to determine whether the resistors that you have manufactured, it is giving you the desired value or not. So you compare it with a standard resistance. Okay, by varying the value of the standard resistance, you want to tune to obtain a balance condition to check that whether that particular resistance is uh, giving you the desired result or not. Other than that, in case of high resistance measurement, you know that you're trying to measure the resistance of an insulating material. So somehow you have an idea about the material that you want to measure. What could be the possible property of that material? Okay, so in that sense, you have an idea that which approach you should go for. Other than that, if you have a particular material that you don't have any idea about, then maybe you have to try for different approaches and try to see which one is actually working for you.
Yes, sir, I got it. Thank you, sir.
Now, regarding your midterm, then how was your midterm exam?